Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Bismillahirrahmanirrahim. Okay, we meet again in this video. So I would like to explain. Okay, this question. This is question June 2016. June 2016. This is actually a question, trust question, and this question is actually for asking for flexibility method actually. Okay, but we look at the trust. Actually, truss or beam or frame indeterminate structure can be analyzed using both flexibility as well as a stiffness matrix method. In stiffness matrix method, we need to identify first number of unknown displacement in the truss. Unknown displacement, because we limit up to 3 degree of freedom for unconstrained system. Okay, so we need to check that first. But before that, okay, I just want to see what is the information given in the question. Okay, redundant. Okay, this is for flexibility, doesn't matter. Okay, there is question. Okay, question C asking for considering temperature changes. Okay, considering temperature changes. Okay, actually, for this question, for this question, if you want to analyze by using information given in question C, because it mentioned about the changes. Okay, temperature up to 40 degrees Celsius. Okay, this is a suggestion only. We don't need calculation. Okay. Okay, doesn't matter. I would like to consider this 40 degrees Celsius, but for certain member only. Okay. So if yesterday, last night we have discussed on thrust analysis, considering fabrication error. Actually, the procedure is same whenever we have temperature changes or fabrication error. We will include Q naught in the stiffness equation. Okay, so but what most important first is we need to identify whether this question, whether this question can be analyzed or not using stiffness equation. Okay, we have to make sure that the maximum unknown displacement in this truss is 3. Okay, so we have here join A as node number 1, node A 1, B, C, and D. And by looking at this truss, there are, okay, we label the element. We have element number 1, okay, element number 2, element number 3, element number 4, and element number 5. Okay, node number in circle. Okay, element number in box. Okay, so for element number, actually we can label which element as A. For example, I label AB as 1. If you want to label AD as 1, doesn't matter. Okay, it is just the matter of position. You can label any number in any element, in any member. Okay, and another thing is we have to put the arrow. Okay, we have to put the arrow. So again, at the arrow also we can put in any direction that we like. Okay, and the arrow is important in order to help us identify near end and far end, because near end and far end is very important whenever we want to calculate Cx and Cy. Okay, this is the arrow for each element which is parallel with the members. Okay, then next one is, okay, degree of freedom. Degree of freedom. So this is the most important part, because we will label, okay, by identifying number of nodes, we can identify number of degree of freedom. But degree of freedom, we need to divide into unconstrained system and constrained system. So total nodes is 4 nodes. We have here 4 nodes, which is equivalent to 8 degree of freedom. Okay. By looking at the support, there are 5 unknown reaction. There are 5 unknown reaction. So in this question at A, there are, okay, 2. At A, representing degree of freedom in constrained system. Okay, another 2 will be put at B, again representing support reaction at the support. So we put here also 2. And we have a roller at C, so this is the direction. Okay, we follow the roller condition, the roller position. Okay, when we put the degree of freedom at roller at C. Okay, and remember that each node must have 2 degree of freedom, because degree of freedom in trust, there are 2 degree of freedom per node. 2 degree of freedom per node means that we have to make sure that each node has 2 degree of freedom. Okay, at A, now there are 2 already. At B, there are 2 already. Okay, at C, okay, it only has 1 now, so we have to put another. One in X direction. So we complete the sign convention, because sign convention in sign convention for degree of freedom. Sign convention for degree of freedom, okay, must be in X and Y direction, because sign convention, this degree of freedom representing will be representing displacement, will be representing forces, because there's no moment in thrust, there's no rotation in thrust. That's why the degree of freedom in thrust we only count in X and Y direction. Okay, and at node D, okay, at or join D, at node D, we have to put another 2 degree of freedom. Okay, so the green arrow, okay, the green arrow representing unconstrained system, and the purple arrow representing constrained system. Okay, each node must have 2 degree of freedom. Total is 8 degree of freedom, because there are 4 nodes, A, B, C, and D. Okay, now we will label. Whenever we label, we should label node. Okay, we should label degree of freedom for unconstrained system first. Okay, because the green label is actually for unknown representing, okay, for green label representing three unknown displacement, okay, 3 unknown displacement, and the purple label, okay, representing 5 unknown reaction. Total is 8, 3 and 5. 3 unknown displacement, 5 unknown reaction. So 3 unknown displacement, okay, is located at C and D. So we should label that. So we label, okay, 1, 2, 3. Okay, we label 1, 2, 3. We have already put, okay, I have already put the label. And after that, continue is 4, 5, 6, 7, and 8. Okay, now we have label all. Okay, so next thing that we need to consider in this diagram is actually the coordinate. Because coordinate is very important, because we need to calculate CS and CY. CS and CY. So we have to put coordinate. So we choose one origin as one node as origin, and I choose B as origin because when I choose B as origin, I will find that A, C, and D will have positive coordinates. Okay, so we continue. So C will be 4 plus 2, 6, 0. Okay, and D will be 4, 3. And A will be 9, 0, 9. Okay, 0, 9. Okay, so once we have this, then only we can start. Okay, we can start to calculate. The first thing here, okay, remember that whatever we do in stiffness, okay, method, is to calculate. The first thing is displacement. Second thing is displacement reaction at the support Q3 until Q8, and then member force. Okay, member force. So whatever we do, we actually we do for Q naught for this. Okay, this is the stiffness equation. Q is equal to KD plus Q naught. Q is equal to KD plus Q naught. So Q naught in thrust will be occurred whenever there is a support settlement effect or fabrication error. Without that, there's no Q naught in thrust. Okay, there's no Q naught in thrust. So we will have this stiffness equation in matrix form, equal to K D plus Q naught. So that is why we do all the process. We do all the process in stiffness method in order to produce this stiffness equation. So there are 8 degrees of freedom. So Q will have 8 Q. Start from position 1 until position A. 1, 2, 3, 4, 5, 6, 7, 8. Okay, K 1, 2, 3, 4, 5, 6, 7, 8. Okay, for displacement also have 8 value. 1, 2, 3, 4, 5, 6, 7, 8. And Q naught also we have to have 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is called as stiffness equation. This is stiffness equation. Why we have stiffness equation? Because from stiffness equation, we will calculate unknown displacement. Unknown displacement. It has boundary here that we determine from, okay, the idea of labeling. Okay, the green label and purple label is actually to divide the system into constrained and unconstrained system. Okay, means that the boundary is actually at 3, after 3, the boundary. Okay, the boundary 3, okay, means that we actually need only this, only this, only this, only this. Okay, in order to calculate unknown displacement. Unknown displacement, because all remaining displacement will be 0, because displacement at support, the position start from 4, 5, 6, 7, 8 will be 0. There's no movement at support. Okay, so displacement, 0 displacement will occur at constraint system. Okay, and for Q, there are five unknown reaction. We have 3 unknown displacement. Okay, so 3 unknown displacement is here, D1, D2, D3. We put as label because we do not know the value yet. Okay, 5 unknown reaction, okay, are Q, Q, Q4, Q5, Q6, Q7, Q8. 5. Okay, unknown displacement. So remaining, we have to put the value for Q1, Q2, and Q3. Q1, Q2, and Q3. 1, 2, 3. Position is 1, 2, 3. So we refer back to the diagram. 1 is 0 because there is no horizontal. Okay, there is no 1. Okay, 1 is 0 because there's no horizontal force at node D. Okay, 2 is negative 150 because it has vertical force at D downward, and it opposite with sign convention. It is negative 150. Okay, at position 3, since there's no horizontal force, okay, at 3, so the value is 0. So it is 0, negative 150, and 0. So it is 0, negative 150, 0. Okay, so now our task is to identify or to calculate this and this. Then only we can calculate or determine the unknown displacement. So we will start with, okay, establish the element stiffness matrices. Okay. Okay, we will start with, okay, element number 1. Okay, we have element number 1, element number 2, element number 3. Okay, element number 3, element number 4, element number 5. Okay, 1, 2, 3, 4, 5. Okay, I highlight. 1, 2, where is 2? This is 2. 2, 3, 4, and 5. Okay, there are 5 elements. Okay, this 5 element. Okay, so I want to, okay, refer to this because I want to take this format. Okay. Okay, so start from this. Okay, we have 5 elements. So this one I need to add insert. Okay, insert below another one. Okay, we choose from this, from this. Okay, we choose from this. Okay, we choose from this and put here. Okay, so first step is not B as origin. So B as origin. Okay, the first thing is okay, we have labeled all the detail in the diagram. So now we want to calculate Cx and Cy for each element. So there are 5 elements: element number 1, element number 2, element number 3, element number 4, element number 5. Okay, so by looking at element number 1, near will be B, near end will be B, far end will be A, because we identify that from the arrow. So to calculate Cx, we will look at the coordinate x, means that it is 0, 0 minus 0. It is 0 divided by L, so the value is 0. Cx is 0. And for okay, for Cy it is 9 minus 0 divided by 9. 9 minus 0 divided by 9, because for coordinate y, we have to look at to y coordinate from near, from far, far minus near. It is 9 minus 0 divided by L, so it will be 1. Okay, so for element number 2, it is near is B, far is C. So it is far minus near divided by length. So for Cx, we look at to the x coordinate. So it is 6. It is 6 minus 0 divided by 6. 6 minus 0 divided by 6, it is 1. And Cy is 0. Cy is 0. And for 3, okay, for element number 3, the length, okay, the length, so wait, I need to take my calculator. Okay. Okay, so the length for member or element number 3 is 2 square plus 3 square root. So it is 3.61. Okay, 3.61 means that for x coordinate, we have to consider x x coordinate for Cx, we have to consider x coordinate from far minus near. So far is 4 minus 6. It is 4 minus 6. It is negative 2. Negative 2 divided by 3.61. Negative 2 divided by 3.61. Okay, it is 0.554. It is negative 0.554. Okay, for cy, it is 3 minus 0. It is 3 minus 0, 3 divided by 3.61. It is 0.831. It is positive. Okay, it is 0.831. 0.831. Okay. Okay. Okay, for element number 4, okay, of course we need to identify the length first. Okay, maybe the best thing here, I need to add another column for length. Wait, I need to add column for length. Insert. Right. Okay. So I want to put L here. L in meter. So length for element 1, the length for element number 1 is 9. Okay, length for element number 2 is 6. Length for element number 3 is 3.61. Okay, for element number 4, the length is, okay, it is 6 and 4. 6 and 4. 6 and 4, so we have 4 squared plus 6 square root. It is 7.21. 7.21. 7.21. Okay, for element number 4, Cx. Okay. Okay. So I need to take break for 5 minutes. Okay, and I will continue after 5 minutes. Okay. Okay, we'll be right back after 5 minutes. Okay, Assalamualaikum. Okay, we continue. Okay, in the previous step, we identify or calculate Cx and Cy, and I have put all the Cx and Cy value for each element in one table. Okay, how to calculate this Cx and Cy? How to calculate this Cx and Cy is by using the formula given as above. Okay, the formula, we determine Ci and Cy from the coordinate. So whenever we want to calculate Cx value, means that we have to look at the x value. Whenever we want to calculate Cx, Cy value, we need to refer to y value. Y value. It is far minus near. Far minus near. We identify far and near and from the arrow. And the arrow is always going to the far end. Okay, towards far end, the arrow. Okay, so for element number 1, for example, element number 1, length is 9 meter. Length is 9 meter. For Cx, it is 0 minus 0. Divide by length is 9. That is why we get 0. So vertical member basically will be 0, 1. Cy will be 1. And the negative or positive depending on the arrow. And for horizontal value, like element number 2, we will get 1, 0. Okay, because Cx will be 1, Cy will be 0. And for the rest, element 3, 4, and 5, since these 3 elements is not vertical, is not horizontal. Okay, so we have the value for both Cx and Cy. For example, for element number 3, far is D. So it is 4 minus 6. 4 minus 6 is negative 2 divided by length 3.61. So we get negative 0.55. And for Cy, it is 3 minus 0 divided by 3.61. So we get 0.83. So we do the same process for element number 4 and for element number 5. Okay, so next step is we need to calculate the element stiffness matrix. Start with element number 1. Element number 1, near node. Okay, doesn't matter. Okay, we look at back to the diagram. Element number 1, near is B, far is A. So from B to A. From B to A, so this is B to A. Okay, Cx, Cy is 1, 0. Okay, from the diagram, so B is 5, 6, A is 7, 8. So the label will be 5, 6, 7, 8. 5, 6, 7, 8. It is 5, 6, 7, 8. It is 5, 6. Okay, 6, 7, 8. Okay, the label is important. Okay, the degree of freedom label is important. It is 5, 6, 7, and 8. Okay, so the value in the matrix, okay, K1, okay, for K1, for element number 1, okay, now we will calculate the value using this formula. So let's do like this. Okay, and this. Okay, for element number 1, so for truss structure, okay, length is 9. Length is 9. Cx is 0, 1 actually, 0, 1, because it is the vertical member. Vertical member, 0, 1. Here is 1. Okay. So Cx is 0 and 1. Okay. So we have like this. Okay, 0 value. Okay. Actually, we don't need to put this. It is just 0. Zero. So this is also 0. And 0. 0. And then we have 0.111. 111. And then 0 again. Okay. And then negative 0.111. 1. Negative 0.111 and then 0. Okay, 0. Actually, that is why I said from, if we compare beam, frame and truss, okay, truss using stiffness method is the easiest. Okay, it's the easiest. 1, 1, 1, 1. Okay, this is 0. This is 0. And okay. So I need to rearrange this. Okay, like this. Okay, full screen again. Okay, this is element number 1. This is K1. This is K1. Okay, K1 in terms of AE, in terms of AE, okay, in terms of AE for a 9-meter length, CX0, CY1. So this is actually the stiffness matrix. The stiffness matrix for element number 1, K1. Okay, so we will do the same thing for another 4 element. Okay, another 4 elements. So I copy this. Okay, so for element 2, okay, we refer back. Element number 2, we have a 6-meter length. Okay, it is element number 2. It is 6-meter length. Okay, for element number 2, B to C. B to C. B to C. Okay, B to C, and it is 1, 0. It is 1, 0. Is 1 and 0. Okay, and the label is, okay, from the arrow, the label is 5 6 3 4. 5 6 3 4. 5 6 3 4. It is 5 6 3 4. Okay, this is maintained. 3 4. 3 4. Okay, this is element number 2. Okay, element number 2, it is 5 6 3 4. 5 6 3 4. So open back this. Okay, doesn't matter. I put like this. Okay, so it is 6 meter length. X is 1, CY is 0. Okay, and we will get like this. Okay, it is 0.167. Okay, like this. 0.167 and 0. Okay, we'll check back later. Is this the right one? Okay. Okay, correct. Okay, so this is for element number 2. Element number 2. So the label is 5634. The label is 5634. Okay, this is the label. Okay, 5634. Okay, doesn't matter. Okay, so we move to element 3 and element 4. Element 3 and element 4. Okay. So for element 3, okay, for element 3, okay, back to this. Element 3, we have 3.61 length, 3.61, and then, okay, negative 0.55 and 0.83. Negative 0.55. It is 0.55 and 0.83 positive. 0.83. Okay. The near is C, far is D. C to D. C to D, from C to D, from C to D, from C to D. So we will put this, okay, in this. Okay. So it is 3.61, negative 0.55, and 0.81. Sorry, 0.83. 0.83. So we get this. Okay, for K3. It is 0.084. It is negative 0.126. It is negative 0.084 and 0.126. 126. And then 0.191, 0.126, 126, okay, 0.126, and then negative 0.191, okay, and then 0.084, negative 0.126, 0.126, 0.191. Okay. Okay, so the label will be, it is 3412. 3412. This is 3. So the label is important because if we don't put the right label, we will get wrong structure stiffness matrix. Okay, the label is very, very important. So the most important thing that we need to, okay, do it properly is the label 3, 4, 1 and 2. 1 and 2. Okay, 3, 4, 1 and 2. Okay, K3. Okay, this is K3. So we move to element number 4. Element number 4. Okay, for element number 4, we have, okay, we need to have, to refer to this back. Okay, it is 7.21, 7.21. It is 7.21. Okay, check again. Element number 4. Element number 4, it is 4 and 6. 4 and 6. 4 square, 6 square, square root 7.21. Okay, 7.21. So it is 7.21 D to A. Okay, it is 7.21 from D to A, D to A. Okay, it is negative 0.55 and 0.83. Okay, so we put into the formula. It is 7.21, 7.21. So we get this value. Okay, it is 0.042. Okay, it is 0.042. Okay, it is actually half of the above value, negative 0.063. 0.063. Okay, so it is negative 0.042 and 0.063. Okay, 0.096. 0.096, and then 0.063, 0.063, and then what's next? Okay, negative 0.096, negative 0.096. Okay, so here is 0.042. The next 0.063, then 0.096. You check. Okay, okay, same. Okay, okay, this is element number 4. Element number 4. Okay, element number 4 from D to A. The label for element number 4, label is 1278. 1278. 1278. Okay, 1, 2, 7, 8. Okay, I copy this. Okay. Okay, it is 1, 2, 7, 8. 1, 2, we label near X, near Y, far X, far Y. Okay, near X, near Y, far X, far Y. Okay, so this is for element number 4. Element number 4. So we have next one, element 5. Okay. For element 5, okay, we only have only one remaining. Okay. Element number 5. Okay, the length for element number 5 is 5 meter. Okay, 5 meter, 0.8, 0.6. Okay, this is 5 meter. Is 0.8 and 0.6. Okay, refer back to this. Okay, from B to D, it is 5612. 5612. Okay, B to D, 5612. 5612. Okay, 5612. B to D. B to D. Okay. And the value is, okay, so length is 5. Cx is 0.8 and 0.6. So we get this. Okay, this value. Okay, it is 0.128. 128. This is K5. Okay, 128. 128. 128. Okay, 0.096. 0.096. 0.096. Negative 0.096. Okay, 0.096, negative 0.096. Okay, 0.128, 0.096, negative 0.128, negative 0.096. Okay, 22 is, or 66 is 0.072, 0.072, 0.72, negative 0.096. Okay, it is negative 0.096. Negative 0.072. Zero seven two 0.096 and 0.072. Okay, 0.072, 0.096, 0.128, negative 0.072, negative 0.096, 0.072, 0.128, 0.096, negative, negative. Okay. Okay, the label will be 5612 because we refer back to this. It is from B to D, from B to D, from B to D, it is 5612. Okay, 5612. So this is element number 5. Okay, this is element number 5. Okay, so we have already determined or established K1, K2, K3, K4, K5. 5 element. Okay, K for 5 element. Okay, if we refer back to this, okay, so basically you need to understand the question given. Understand the question given. If the question asks you to give stiffness equation, okay, establish stiffness equation for the truss. So this will be the answer in full. Okay, if there's no question mentioning about stiffness equation for the truss, okay, it only asks you to calculate unknown displacement. So actually we don't have to establish in full. Okay, establish in full. We just need to have stiffness equation corresponding to unconstrained system in order to calculate unknown displacement. Means that we will focus on this only. It is 3 by 3 matrix. 3 by 3 matrix. This is D1, D2, and D3. And plus with this. Okay. So if we don't consider temperature changes, then there will be no Q naught. No Q naught. Okay. So now we want to focus to the stiffness matrix, but I want to highlight on this 3 by 3 only. 3 by 3 only. So this is 0, negative 150, 0. So now I want to fill in this matrix. Fill in this matrix. So we go back to this. Okay, wait. I want to find the stiffness matrix or stiffness equation. Stiffness equation when we have three. This is only 2. Okay, doesn't matter. So I just copy this. I will copy the whole thing, duplicate. Okay. Okay. So for the stiffness equation, the basic stiffness equation without considering temperature changes or fabrication error is like this. Q is equal to KD. For our question, we have the boundary after 3. Okay, the boundary after 3 like this. Okay, the boundary after 3. So we have negative 150. And actually, you don't need to give 150. Okay, in full like this, whenever the question is not asked you to do that. Okay, but still, you need to have this in your mind. Because if you spend time doing this and the question don't ask you to do that, you are just wasting your time. Because we need to focus only at 3 by 3 matrix. Means that from 1 1 until 3 3, 1 1 until 3 3. So this, I will not identify all value. I will not show to you all value. I just want to focus on, wait, I just need to copy this. So we will have 3. Okay, D3. Okay, this is D3. Okay, so this is stiffness equation in full without considering effect. Okay, I just want to show to you the important part here is only okay, this, and this. Okay, so actually we don't have to write in full. So what we need to have is actually the stiffness equation corresponding to unconstrained degree of freedom system. So I want to actually okay, focus on the below part. Okay, the below part, this one. Okay, and negative 150. So need to add another column. Insert after. Okay, this will be 0. And then insert as well. This will be D3. Okay, D3. D3. Okay, so this is AE. Okay, and the matrix is 3 by 3 matrix, so I need to add after. Okay, and the value we will get from the above element stiffness matrices. Okay, forget about the upper part. Okay, we just need to focus on the below part where we need to consider Q is equal to KD. Okay, here is stiffness equation. Stiffness equation corresponding to unconstrained degree of freedom, unless whenever we have support settlement. Okay, because whenever we have support settlement, we have to consider at the settlement position as well. Okay, here we need to consider only stiffness equation and in unconstrained degree of freedom system, because in constrained system all displacements are 0. So we just need to consider from 1 to 3 like this. So we will determine the value for 1 1 from K1, K2, K3, K4 and K5. So let's do it now. Okay, 1 1 1 1, there's no 1 1 from K1 and K2. Okay, 1 1, okay, we have 1 1 here from K3. It is 0.084. 0.084. This is K4. Okay, 11 is 0.084, and we have another 11, okay, in K4, and it is 0.042. Okay, let's check. Do we have 11 for element number 5? So we have 0.128. So position 11, the value is 0.254. 254. Okay, now I want to show to you if we don't consider temperature changes, the basic equation Q is equal to KD. So after this, I will show to you how we include temperature changes in stiffness equation. Okay, it is 0.254. So next position is 1, 2. Next position is 1, 2. So there's no 1, 2 in element 1 and element 2. We move to element number 3. 1, 2. 1, 2 is negative 0.126. Okay, this one. Negative 0.126. 1, 2, we have negative 0.063, and 1, 2, we have 0.096 plus, okay, this is the value, 0.096. 0.096. It is negative 0.093. Negative 0.093. So focus on the below part only. Okay. Okay, I will do it like this. Okay, so I will delete this. And this. Okay, it is stiffness equation corresponding to degree of freedom system. Corresponding to degree of freedom system. Okay. Okay, this is stiffness equation corresponding to unconstrained degree of freedom system, because we only need this to identify the unknown displacement. Okay, this part, I will not consider the temperature changes first. Okay, we focus on the basic equation Q is equal to KD. Okay, so the next value is 13. So we find the value 13 value from K1 until K5. Okay, there's no 13 at K1, K2. Okay, 13 we have here, 13 negative 0.0. It is negative 0.084. Okay, 13. And there's no 13 in K4, and there's no 13 in K5. It is 0.084 negative. Negative 0.084. Okay, the next value is, okay, we complete all this. Negative 0.093. Negative 0.084. Okay, the next value is 22. Okay, 22 start from K3. Okay, it is 0.191 plus 22 is 0.096 plus Okay, we have 2 to 0.072. 0.359. 0.359. 0.359. Okay, and for position 2, 3, okay, for position 2, 3, so where is it 2, 3? Okay, here is 0.126. Okay, there's no in K4. Okay, it is only 0.126. 0.126. 126. And 3, we find in KK1. Okay, 3, we have 0.167 in K2. And after that, K3, we have 0.084. And then we have, okay, only this. It is 0.251. 0.251. Okay, so this is stiffness equation corresponding to unconstrained degree of freedom system, the basic equation Q is equal to KD. So this part we can straight away solve for the unknown displacement because this is the three equivalent to three simultaneous equation. Okay, but okay, let's say we want to consider the temperature changes. When we want to consider the temperature changes, what we need to do is we have to, if, okay, let's say I copy this first. Okay, plus Q naught, plus Q naught, Q naught, okay, considering temperature changes. So to consider temperature changes, we have to include Q naught. Okay, the basic equation, no temperature changes, no fabrication error, it is just like this. So because whenever we have this, okay, this equation we can solve for unknown displacement. Okay, just using calculator, determine D1, D2, and D3. However, if we have to consider temperature changes, we have to add Q naught. Okay, we have to add Q naught. And we have to put the value. Because temperature, either temperature or fabrication error will influence the output. Okay, will influence the output. Okay, means that we need to identify or calculate the value of Q naught at position 1, at position 2, and at position 3. Okay, we have to consider this because in the upper part there's no Q naught, so we have to consider Q naught, okay, for this. And okay, this, okay, now is 7:16, so I will continue this part. Okay, wait. I will continue this part. Okay, in class after this. Okay, in class after this, I want to show to you the difference whenever we just have the stiffness equation without effect of temperature, without effect of fabrication error. Okay, so the upper part is the direct solution, Q is equal to KD without effect, any effect. And the lower part is whenever we need to consider temperature changes. So that value, okay, the blue circle that which I highlight as blue, okay, I will show to you how we include this temperature changes. Okay, temperature changes into the stiffness equation in order to calculate unknown displacement for this thrust question. Okay, so this part I will continue in the next video. Okay, next video after this video. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Okay.